So I have begun recording. Upcoming webinars, next week, the 22nd, we have improving worker health through organizational changes. And you can register for that and other upcoming webinars at coeh.berkeley.edu/webinars. That's coeh.berkeley.edu/webinars. For today's webinar, you will be muted during the presentations. There are 2 speakers today. If you'd like to ask a question, please enter it into the online Q&A, and we'll save some time at the end of the presentation to address your questions. As I mentioned, part of the first half of the webinar is being recorded. The second half will be live only. You can go to our COEH Northern California YouTube channel to see this recording and past recordings. Please like and subscribe to our channel and help us grow. Today's webinar is titled Ergonomics Research Updates from the University of Michigan. It will be presented in 2 parts. And the first speaker today is Kamolnat, also known as Cam Tabattanon. And she is a PhD candidate working with Dr. Bernard Martin at the University of Michigan within the Industrial and Operations Engineering Department. She's been working in areas of universal and inclusive design since her master's in mechanical engineering at Oregon State University. Cam is an OSE NIOSH trainee at the Center for Occupational Health and Safety Engineering at the University of Michigan. And after Cam, we also have Karanveer Panesar, and he is a PhD candidate in the Department of Industrial and Operations Engineering at the University of Michigan. His research explores how frequent interruptions affect performance of operators controlling multiple unmanned autonomous vehicles and develop guidance for the design of interfaces that support the efficient integration of a large number of interruptions. His other research interests include human-machine trust and aviation safety and disturbance management. He has a background in computer engineering and art. Before starting the PhD program, he worked as a software developer and user interface designer with a focus on developing ground control station software for facilitating human teaming with aerial and ground-based autonomous systems. All right, and with that, I'm going to hand the mic over to you, Cam.
All right, volume all right?
Sounds great.
All right, thanks so much for the introduction, Alan. I am very honored to be here. So with that, let's go ahead and get started. The learning objectives for my talk will be to increase your awareness of the impact of inclusive mobility design within workplace environments, how and why population subgroups must be considered towards improving inclusion, potential biases caused by simulated impairment, which is a common practice within usability testing, and that environmental interventions can increase workplace inclusion, but do not necessarily involve large-scale construction. Let's start with the basics. What is inclusive mobility? Well, breaking it down, mobility refers to an individual's capability to move from one point to another, and inclusion strives to support the spectrum of human capability. For this talk, we will focus on individual spatial mobility. So think along the lines of maneuvering within or between rooms. And I want to note first off that the images and what I say in this presentation will focus on inclusion for mobility limitation, specifically that of manual wheelchair usage, but inclusion as a whole does span the greater range of needs. I just want to make that clear. I also want to clarify the difference between accessibility and inclusive systems. Accessibility provides alternatives for participation upon request. And this is something like public transportation and most grocery stores we might be familiar with, while inclusive systems strive to provide a spectrum of tools and make them readily available towards equitable participation. That equity is an important key difference here. So then why is inclusive mobility relevant to ERC research? Simply because inclusive mobility impacts workers across numerous fields. Some examples are listed here, and you can imagine a task like moving between pens or machineries like these images, and obstructions like this can result in both injury to the workers and damage to equipment, which might be very expensive. So in that perspective, inclusive mobility is not only important to worker health, but also benefits the employer as well. And right now is a crucial time for research and development in this area because more people are going to be impacted by reduced mobility in the coming years. In particular of concern, especially for this project, are older adults. We're seeing that 20% of older adults currently wish to work into older age within the United States, and this is either by choice or due to financial or other reasons. And the aging population is reporting an increasing trend in disability, most commonly mobility disability. And with the current state of work as it is, nearly a quarter of older adults with disabilities who are looking for work cease their efforts due to discouragement. And the reason we've narrowed down mobility disability to manual wheelchair usage, as I mentioned before, is because there is a projected increase in its use within this population, what that already makes up the largest user group. Over 60% of older adults who currently use a manual wheelchair report difficulty in use, and almost half are not as independently mobile as they desire. And without the proper support, older adults will need to increasingly rely on unpaid caregiving services. This is a projected trend to increase, and this can negatively impact not only the individual, but the caregiver and society's economics and working effectiveness as a whole. So then the question becomes, how can ERC research address this challenge and promote sustainable inclusive mobility? Well, the method we propose is that through the investigation of space and action perception, we hope to determine ways in which the task environment can be improved, not only to support motor execution that is involved in mobility, but through the mitigation of perceptual uncertainty of capability in action. So that's a lot of sciencey words. So let's talk about what that means. And hopefully you can see my mouse. Let's start at this guy right here in this image. Before you execute any action in spatial mobility, you perform a cursory glance at what you're doing and an initial perception of your navigation space. This is driven by your top-down perception, incorporating your capability, the spatial constraints, and the task at hand. So this is the task environment in human factors. And with that top-down prediction, you create an internal motor program, which functionally this tells your muscles what to do and tells your sensory motor system what to look out for. You execute that command, and then your sensory motor system provides you bottom-up information feedback on what you just did. You adjust your actions accordingly, and you repeat this process until your goal is met. So for example, let's say you're moving on ice and it's super slippery. You want to make like a tiny movement, but you make that initial movement and you end up going further than you expect. So for the next cycle, you're going to make an even smaller movement to reduce that discrepancy and actually make the movement you want. That is essentially what we're talking about here. And we are investigating ways to support both this top-down and bottom-up process towards inclusive mobility. Specifically, we investigate the internal representations of motor action by that little spiral image on the previous slide via measurements of mobility before, during, and after a path-following task. And we're using a path-following task because it's analogous to moving through furnished or obstacle spaces. So for example, an office worker moving through a hallway or a retail worker moving through a grocery store with all those movable baskets near the checkout. We're also interested in group differences between commonly used convenience groups, and these are groups that are used in both research and usability, to determine how such groups might bias outcomes. And the two groups that we are investigating are incidence period and simulated impairment. We'll talk about them in turn, but let's start with incidence period. And this specifically is incidence period of manual wheelchair usage. So either folks who age into or with their mobility limitation. What commonly happens is older adults are recruited for studies or usability testing with a convenience sample. So whoever can show up will show up, or by a medical condition. But the literature shows that this likely creates a bias, since in a convenience sample, stronger people are more likely to volunteer. And with a specific medical group, they are expected to experience a certain type of rehabilitation all around. Recently, it's also been shown that the age of incidence can also bias the provider on recommendations towards training types. So here we use an ICF framework to see what we can expect with different incidence periods, and we anticipate that to impact functional capability, sensory motor perception, and internal motor representation. The last two items of interest, we expect to impact the perception of space, capabilities, and performance, which then can impact confidence, safety, and participation. So what we've done is we've designed a study in order to investigate the group differences between incidence periods in order to determine how and where the different levels of mobility support may be needed between these two groups. The task itself, as I alluded to, is a path following task within constrained walls. We recruited volunteers aged 50 plus with no significant uncorrected visual, cognitive, or spatial neglect impairments, and without upper extremity loss or prosthetics. We use adjustable mock-up panels made of cardboard, and I want to highlight that we use cardboard in order to reduce risk of injury, but also to reduce the impact that discomfort might have subjectively, because volunteers might experience lower extremity arthritis or skin sensitivity given our age group. For this task, we asked participants to move from start to finish within the path as quickly as possible while prioritizing safety. We also asked them to imagine that the cardboard walls are actually hard walls, like real walls in a building. So collisions would hurt. So we've asked them to avoid collisions as a part of prioritizing safety. And in order to look at that top-down and bottom-up perception that we're interested in, we divided the task into 3 phases, like you see here. In the before task, participants rely on visual senses and top-down perception to respond to some NASA TLX scales on how they believe they will perform. During the task, we use EMG and IMU devices to quantify mobility in terms of muscle activity, path taken, and critical events. We use muscular activity because it can inform motor control and activation, and these can be related to the affective capability, which again is something we expect to be different between these groups. We do realize in the study design that in a lot of usability testing, the use of biometric data can be very costly and unrealistic for a lot of projects, but we are using EMGs in this case to imagine the validity between the convenience groups. And finally, in that after task phase, participants rely on their sensory motor and bottom-up perception to respond again to the NASA TLX scales to let us know how they believe they performed. And all 3 of these phases are analyzed and compared. Today, we're going to focus on some preliminary results, looking at scales of frustration and collision counts for the critical events, and specifically dominant and non-dominant handed turns. We use hand dominance for turns rather than lefts and rights to make results more comparable between individuals. So let's look at some results. Our preliminary sample is described here. We used a dichotomous cutoff of 45 years for incidence period rather than using years of experience. And in brief, the reason we did this is because of what we know about motor training and capability as we age as humans. So like 10 years of experience would be different for someone who started using a manual wheelchair when they were 40 versus someone who started using a manual wheelchair when they were 60, right? So this graph shows the expected frustration between the 2 groups when asked, how do you think you will perform? How do you expect to perform before the task? So these colors are supposed to be colorblind friendly, but just in case they're not, the dominant handed turns are shown on the left for either group. The later in life group, labeled the LL group, communicated a greater range of expected frustration compared to the earlier in life group, EL. And that's again, folks who started using a manual wheelchair before and after the age of 45. Both groups, even though the LL group showed a larger range, had comparable expected frustration levels. However, only the LL group anticipated failures, and they also expected more collisions on more tasks. So far within that motor action process, again, recall that little image with the spiral, both instance groups seem somewhat comparable with some lower confidence from the LL group. Now then, how did we, the researchers, quantify their performance? We observed a greater number of collisions committed by the LL group, and hand in hand with that, we also noted longer task times by the LL group, correlating with the number of collisions. So here we're starting to see a deviation between the groups in the motor execution phase. And what's interesting is given the longer completion times with the greater number of collisions, this also suggests perhaps a different bottom-up correction process as well. So now, how did the volunteers think they performed? Again, the LL group communicated a greater range of perceived frustration, still comparable to the EL group. And some bonus metrics for us to talk about. The LL group perceived comparable levels of performance quality and level of task difficulty compared to the EL group, but a greater degree of effort required to complete the task. So then what we can do is compare these phases together. And our results support the hypothesis that the LL group may experience mismatches within their internal motor representation, which is evident by their more erroneous performance, but stating that they perceived comparable performance quality. And this aligns with the literature that historically excluded populations can underrate their own challenges, which can bias traditional rating systems that are largely subjective. A phrase we heard a lot when talking to our participants is, well, I did manage to finish, therefore my performance is good. And this idea circles back to what I mentioned at the beginning about accessible systems versus inclusive systems. Most people are familiar with accessible systems where the goal is participation, not equitable participation. And regarding the usage of convenience samples, our results suggest that by not actively recruiting a population that might struggle more with the task, we can be excluding a subgroup that is very key towards inclusion. Before I move on to the next slide, I do want to note that our preliminary sample is notably small. We recruited during 2021 and 2022 during the waves of COVID-19 with many health and safety precautions in place. The trends that we show in our analysis have rather high effect sizes, but still we do intend to reopen recruitment. Now I'd like to pivot to simulated impairment. A brief introduction for those who might not be aware. Simulated impairment refers to the interactive role play used to simulate capability loss or limitations. And most commonly, the goal for simulated impairment is to increase an understanding towards people with disabilities or older adults with target audiences like students, healthcare providers, and designers and practitioners. And you might be able to imagine the answer to this question, but why would simulated impairment be used rather than recruiting older adults with disabilities? From the validity standpoint, there currently is there remains a strong assumption that as a tool, role-playing can accurately capture the disability experience. And practically, projects have time and budget constraints. So designers will try to temporarily represent their users who are otherwise difficult to access. And this can take place in early ideation, the creation of, let's say, the house of requirements, or in lieu of adequate stakeholder meetings. Alan mentioned this, but my own background is in mechanical engineering design. So I understand the pressures towards wanting to use simulated impairment, but it is also very important to understand the implications of using a tool like this if we do decide to use it. Particularly, simulated impairment has been found to have many negative impacts in terms of emotional reactions, stereotyping against these populations, and attitudes. There are many disability studies, papers on this topic, but not so much in terms of the impact on design. So for our project, we will examine the impact of simulated impairment on physical performance measures for our target population, i.e. we test the validity of simulated impairment on a manual wheelchair mobility task. For this study, we used a parallel parking test. We asked participants to start next to and slightly behind a rearward block like you see in this image here. Then in a self-paced and self-selected maneuver, participants move between the blocks into essentially a parallel park. Researchers will watch their movements from the other side of the room, and if a collision is noted, then the participant is informed and the space is moved out slightly and the trial is repeated until a minimum clearance to do this park is found. Same population was recruited as the last study, age 50 plus, no significant uncorrected visual, cognitive, or spatial neglect impairment, and no upper extremity loss or prostheses. I want to show you guys some preliminary results for that. The graph shows the minimum clearance required to perform the task by group. We found a significant difference between the clearance that was required, and somewhat unexpectedly, the simulated impairment group actually required less space than the wheelchair user group. I also want to note this last row here in the table, that the wheelchair user group had a lower occupied depth. And this is due to a handful of participants in this group, but not all, using their own personal wheelchair for this task, since we didn't allow transfers for safety reasons. Given that these devices were smaller and more customized, if this were to have biased the results, we would have expected the wheelchair user group to require less space compared to the SI group. However, that is not what we found. So these results overall imply that if we had used SI for usability testing on this design, a smaller than adequate space may have been recommended towards accessibility. And again, I want to note that we are trying to increase the sample size with ongoing work. We've kind of put ourselves in a little conundrum because we're trying to investigate the impact of a convenience sample. And we are then trying to recruit a sample that is quote unquote inconvenient by comparison. So yes. Now, towards wrapping up, I just want to summarize the implications in the work that I've shared with you guys today. In terms of the incidence periods, we found that people aging into manual wheelchair usage had different motor action and performance perception compared to their age-matched peers who aged with usage. And as a consequence, these groups likely benefit from differing types of supports. I was able to finish the task, so my performance went fine, is actually a finding that we also saw in previous work related to autonomous shuttles. This is not a singularity. Now regarding simulated impairment, we found that while this tool can be attractive, its use can actually bias even non-subjective measures. And biases can often result in inaccessibility, and inaccessibility might be dealt with patchwork accessibility efforts like we've seen in transportation. Now, before I finish, I want to circle back to the challenges I presented at the beginning of my talk. What are our expected project outcomes towards addressing mobility inclusion then? In ongoing studies, we are investigating environmental interventions to see how we can support that top-down and bottom-up motor action. Our manuscript is currently in process, so I don't have specific photos included, but general examples are simple signage and markers within the environment. None of the things we are investigating require large-scale construction or alteration of architecture, and that was very important for us going into this project. And one question I get a lot when talking about this project is, why are we focusing on environmental interventions when options like training or modified mobility aids are available? Autonomous wheelchairs come up a lot in conversations now. And the answer focuses on largely burden and issues of sustainability. So person-oriented interventions are things like training or manual wheelchair customization, like that automated feature I mentioned. And these options are able to improve confidence and skill, which have been studied in the short term, but they have low retention rates and little studied long-term effects. In general, they are limited and subject to socioeconomic inequity. So essentially what this does is it puts the burden on the user or the worker to obtain their own intervention. Environmental interventions, on the other hand, might include things like assistive indications in the environment or geometric adjustments. And I really want to emphasize that these do not necessarily mean like rebuilding your built features. Multiple participants who came in actually shared stories about the psychosocial impact of having to ask other people in a restaurant to move for them to access their table because there was not enough space between the tables. So like spacing those tables out counts as a geometric adjustment within the space. Implementation of environmental interventions can provide long-lasting support that is available to everyone within that space. There might be a higher initial cost, but the burden of cost does not fall on the user or worker. Spatial adjustments like moving that restaurant table could negatively impact overall occupancy. And accessibility standards can actually be insufficient because we have a changing population, and a lot of the standards are prescription-based, not performance-based. But as human factors professionals, we know that the task environment should inform the user needs, which is why our study hopes to use performance-based measures towards recommendations. I'd like to acknowledge and thank my colleagues in our sensory motor systems and human vibrations lab at the University of Michigan, as well as the Center for Disability Health and Wellness and the Center for Ergonomics. Everyone's continued feedback and support in this research project has been greatly appreciated. And for my final slide, I just want to leave you guys with some key takeaways. I believe our work is highly relevant and important to ERC research because inclusive mobility impacts the task environment, including at workspaces. Who we recruit in both research and usability testing can bias these designs. And to ensure inclusion, we recommend identifying and recruiting user groups who might experience greater difficulty in the task that you're interested in. Our ongoing study investigates ways to support top-down and bottom-up perception within mobility. And we hope that our simple interventions can make it accessible for businesses to provide inclusion. I'd like to thank NIOSH and the University of Michigan Center for Occupational Health and Safety Engineering for their support through the PPRT grant and OSC traineeship, as well as Bracken Graduate School for their research grant support. With that, Alan, I am all finished, and thank you all for your time.
Thank you, Cam. That was really interesting. Thank you so much.